Raasika, lecturer of BCA from Milagres College. So here we are discussing about switching techniques and data link layer. First one, switching. In networking, switching refers to the process of directing data packets between the devices on the same network. Switches operates at layer 2 of the OSI model and the use of MAC address to forward data to the correct destination. So there are two types of switching. First one is packet switching. Conceptually, when you or your computer places a telephone call, the switching equipments within the telephone system seeks out a physical path all the way from your telephone to the receiver telephone. This technique is called as circuit switching. So there will be a carrier switching office. So an important property of circuit switching is the need to set up end-to-end path before any data can be sent. The elapsed time between the end of dialing and the start of ringing can be easily 10 seconds, more on long distance or international calls. So these are the carrier's offices, and these are the signals, that is incoming signals, and these are outgoing signals. There are signals passing through one box to the other box. So these are establishing physical connections between the carrier offices. So this is circuit switching and this is packet switching. Packet switching. With this technology, packets are sent as soon as they are available. There is no need to set up a dedicated path in advance. It is up to the routers to use store and forward transmission to send each packet on its way to the destination on its own. So this procedure is unlike circuit switching, in which the result of connection setup is the reservation of bandwidth all the way from the sender to the receiver. With the packet switching, there is no fixed path, so different packets can flow in different paths, depending on the network condition at the time they are sent, and they may arrive out of order. Packet switching networks place a tight upper limit on the size of the packet. It also reduces the delay since the first packet of long message can be forwarded before the second one has fully arrived. So here we are not setting up any dedicated path from the sender to the receiver as we are doing in circuit switching. So here the router itself, it will provide a dedicated path from the sender to the receiver. Next one is data link layer. These are the services provided by data link layer. So first one is providing a well-defined service interface to the network layer. So network layer is a layer which is next to the data link layer. So if there is any error in the network layer, means packets, this data link layer will be helping. Next one is dealing with the transmission error. As the data being transferred from the physical layer to the application layer, there may be any kind of errors in the data. So in order to detect or reduce that error, this data link layer is used. Next one is regulating the flow of data so that slow receivers are not swamped by the fast senders. If there are senders who are sending the data very fastly, if that is not acceptable by the receivers, that time the receiver will be flooded with the data. So in order to eradicate or reduce these kind of things, the data link layer is helpful. Next one is error control. So how to make sure all the frames are eventually delivered to the network layer at the destination and in the proper order? The usual way to ensure reliable delivery is to provide the sender with some feedback about what is happening at the other end of the line. So typically the protocol calls for the receiver to send back a special control frames bearing a positive or negative acknowledgement. So here in error control, what happens is, in order to know whether the frames are being transferred to the correct destination or not, what we need to have is feedback. So when there is a feedback from the receiver saying that the errors means the data is being received or not, we will come to know the surety about the data. If the frames or the data being received by the receiver, they will send a positive acknowledgement saying that we have received your data. If the data or frames are not received by the receivers, they will send the negative acknowledgement saying that the data which you sent is not being received. This is the use of error control. Next one is flow control. So what to do with the sender that systematically wants to transmit frames faster than the receiver can accept them? So this situation can occur when the sender is running on a fast, powerful computer and the receiver is running on a slow, low-end machine. Even if the transmission is error-free, the receiver may be unable to handle all the frames as fast as they arrive and will lose them. So if the receiver is using the low-end machine or slow machine, what if the sender is using the fast machine? Means the receiver will be flooded with the data. So in order to eradicate or remove this type of problem, we are using two types of approaches. One is feedback based control. So the receiver sends back information to the sender, giving it permission to send more data, or at least telling the sender how the receiver is doing. Next, in the second one, rate based flow control. The protocol has built-in mechanism that limits the rate at which the sender may transmit data without using the feedback from the receiver. Next one is simple parity checks. So these are the error detecting techniques. So in simple parity check, one extra bit is transmitted in addition to the original bits to make the number of ones even in the case of even parity or odd in the case of odd parity. So while creating a frame, the sender counts the amount of ones in it. If even parity is utilized and the number of ones is even, one bit with the value 0 is added. In this manner, the number of ones remains even. If the number of ones is odd, the value of 1 is added to make it even. The receiver just counts how many ones are there in frame. If the number of ones is even, then even parity is utilized. If the frame is regarded as uncorrected and approved, even if the number of ones is odd and odd parity is utilized, the frame is not damaged. So here the sender is sending data, means 1000111. After computing the parity bit, what we will come to know that there are odd number of ones, means only 3 numbers are there. So means that is odd. So if there are odd number of ones, we are adding 1 to that, sending through the transmission media to the receiver. So what is the receiver does is, he will compute the parity bit of this data. He will check for number of ones. If the number of ones are even, he will accept the data. If the number of ones are odd, he will reject the data. If here only if the number of ones are even, we are adding here 0, means the data will be accepted. Next one is two-dimensional parity check. For each row, parity check bits are calculated, which is identically to the basic parity check bit. For each column, parity check bits are computed and transmitted together with the data. These are compared with the parity bits calculated on the received data at the receiving end. So here we are sending frames like this. So here we are checking row parities and column parities. So as we done in this, the same thing will be doing here also. Like we are checking number of ones. If the number of ones are even, we are adding 0 here. Here also there are number of ones are even, so we are adding 0. All these are zeros because all the number of ones are even. So here we are calculating column parities 1, 2 and 3. Means number of ones are odd, we are adding 1 here. So like this we are calculating the row parity and column parity of this check bits. Now the data that has to be sent from the sender to the receiver is this one. Next one is checksum. The word checksum is often used to mean a group of check bits associated with a message regardless of how are calculated. A group of parity bits is one example of checksum. However, there are other stronger checksums based on running sum of the bits of the message. The checksum is usually placed at the end of the message as the complement of sum function. This way, error may be detected by summing the entire received code word, both bits and the checksum. So this is the example of checksum. So the number of frames are 4, means we are naming it as K4. K is 4, means number of frames are 4. Then the number of bits are 8. In each frame we have 8 bits. These fully we are saying it as frames and these are bits. So number of bits is 8. So we are calculating from the sender side, means we are adding these two frames, this first frame and the second frame. We are calculating the value 1 plus 1 is 1, 0 plus 1 is 1, 0 plus 0 is 0. Like that we have to calculate, means we have to add the two frames. If 1 plus 1 is 0, we have to make 1 as a carry here. And we have to take this carry this side and we have to add it to the sum. Next, it comes like this and we have to add the third frame here. So, after doing the summation, we are getting this as a sum. So, in order to get the checksum, what we have to do is, we have to take the complement of this sum. Means, if it is 0, we have to make it as 1. Means, in the place of 0, 0, 1, 0, 0, 1, 0, 1, we have to make it as 1, 1, 0, 1, 1, 0, 1, 0. For the same thing, we have to do it for the receiver also. So, here what happens is, up to sum, we have to do it as same. And later we have to calculate these two here. We are calculating sum with the checksum. Means we are getting the value as ones. After taking the complements, if there is even numbers, means the data is being accepted, or if there is odd numbers, the data is being rejected. This is checksum. Next is cyclic redundancy check. So the CRC means cyclic redundancy check, also known as polynomial code. Polynomial code are based upon treating bit strings as representations of polynomials with the coefficients of 0 and 1 only. The sender inserts reminder at the end of the original bits before sending the actual bits. The code word is made up of the actual bits plus the reminder. The transmitter sends the data from the code words. The receiver, on the other hand, divides the code word using the same CRC divisor. If the reminder consists of entirely of zeros, the data are validated. Otherwise, it is assumed that some data corrupted happens during the transmission. So this is CRC. So this is the original data to which we are adding the numbers, means number of zeros. So divisor, we are calculating CRC through which we are sending the data with the CRC, means with the reminder. We are adding it and sending it to the receiver side. And after that we are again dividing it by the divisor, and if we get the reminder as 0, means it is accepted. If we get as odd numbers, then it is rejected. This is an example. So we will get this polynomial or any other polynomials. So if it is x to the power of 3, we have to make it as 1 into x to the power of 3. The two x to the power is x square and x to the power 1 is not there. So we have to write it like this. And the first number is counted as the divisors, means 1, 0, 0, 1. So to which we have to divide. So these are the original numbers. So the number of divisor we have is 4. So here what we have to do is n minus 1, means 4 minus 1, that is 3. 3 number of zeros we have to add it here. So after that we have to calculate and we have to use XOR operation, means 1 plus 1, that is 0, 0 plus 0, that is 0, 1 plus 1, that is 1 plus 0, that is 1, and 0 plus 1, that is 1. And remaining zeros we have to add it here. Next, the same thing we have to write it here and do the calculation. Later we will be getting this as an answer. So the last 3 numbers will be added to the original data and sent to the receiver side. So in the receiver side also we are doing the same thing, and if we are getting the reminder as 0, the data is being accepted, or if it is 1 or some odd numbers, the data is rejected. Thank you everyone.